In this episode of The Rocks of Utah, we're going to search for the mother of all extinction events, the Permian-Triassic extinction, and see if we can reconstruct the events that led to this mass extinction here in Utah. This is big picture stuff, the collection of many observations over hundreds of years of fossil collection. Many facts stacked on top of each other, but we'll only discover more of them if we know where and how to look for them in the rock record. Today we're going to a place that I believe has the greatest chance of preserving this boundary layer. We're going to look at the contact between two lithologically defined formations, the late Permian Park City and early Triassic Dinny Wood formations. Now today I am right where the Paleozoic and Mesozoic rocks meet at the boundary layer. So this ridge of rocks that I'm interested in studying, this thick set of rocks, and actually even the rocks beneath my feet, they show a major transition in their fossil record. And right now I'm at the edge of the last of the Paleozoic and the very first of the Mesozoic rocks. But I need to sample these rocks in detail to document the changes that are happening across this boundary layer, and hopefully prove to other scientists that this really is the boundary that represents the Permian-Triassic extinction event. During the late Permian, about 252 million years ago, Utah was on the western coastline of a passive margin of the giant supercontinent Pangaea. Western Utah was within a deep marine basin, while southern Utah was dominated by an almost eroded away mountain range called the Uncompahgre Uplift, which extended east-west across eastern Utah and western Colorado. Here in northeastern Utah, north of the mountain range, was a broad, shallow inlet for the ocean, and it left behind a phosphorus-rich rock layer of carbonate rocks that represent a tropical coastline of a once biologically rich reef complex. We're really, really close to the boundary layer. And I've dug it down until I hit the really resistant Park City Formation, which is this stuff here. This is actually the top surface of the late Paleozoic right there. And then starting here, I'm going to take samples in the early Dinny Wood. We're going to take samples every 5 centimeters as we go up this. Pretty high resolution sampling. There's still quite a bit of roots in here, but I'm hoping I can get into the rock. This lower part here is a mudstone, which is kind of what they've observed in China at the Permian-Triassic boundary. So we're going to sample it, and we're going to work our way up the section and record our observations, probably a couple meters. This will be the first meter, will be about here, and then we'll probably sample another meter or two, and then take some samples on top of the ridge to make some comparisons with. So, so yeah, let's get some sampling done. One to that point. We're gonna call that 2 meters. So I thought I'd take you through a little bit of what I observed in the rocks as I was measuring the section and measuring the samples and collecting the samples. So at the very base, we have a limestone, and right on top of that limestone is kind of a bumpy surface. And then right on top of it is a mudstone. And this mudstone is a very base of the Dinnywood, so the very base of what's supposedly the Triassic. And what's interesting about this is it's very soft and crumbly. I had to dig really far back in to get a good sample of it, because it's very poorly cemented, and it's a mudstone kind of clay stone, which is interesting. It seems to indicate it has very little carbonate. We'll verify that back at the lab. So then as I moved up, I got to about 86 centimeters up, and I started encountering some iron oxide concretions, and a little bit of gypsum that was in there. Then it becomes more silty, more carbonate, seems more white in color. Around 1.5 meters above the base, I get into black nodules, little black nodules. I'll find out what those are. And then about 1.7 meters, we start getting some good sedimentary structures. And these sedimentary structures are actually really fascinating. And I actually got some right here. I don't know if you can see these. In fact, actually, grab this piece. This has some really nice ones in it. And I think that was the top. So these sedimentary structures are interesting because they're little cross-bedded. They're bilateral, which indicates that they probably are oceanic instead of fluvial. And the other cool thing about these little sedimentary structures is that we see them very similar to this in some of the tidal flats, where you have like a mud or very silty substrate, and then the waves come in and waves go out in a tidal sequence. So a tidal flat. And where you see these sedimentary structures today is sort of along the coast of the Netherlands, or along the Baltic Sea, or where you have a passive margin, where you have these big, huge tidal flats. They're very barren. They can support organisms, you know, burrowing clams and things like that. So hopefully you can find some of those up here. But we start getting those sedimentary structures in. Below, it's very blocky, no sedimentary structures that I could see. So very blocky sedimentary structures are tidal flat deposits. And then you get a lot more iron concretions. And then it's also harder rock, like it's more well cemented. So you're starting to get rock that starts to form, you know, like these kind of cliff edges around up here, they're a little higher up in the Dinnywood than I sampled. But basically you start getting a little bit more resistant rock, and it's more shaly. So it breaks in flat plains as you get higher up. So what's really interesting is this little mudstone layer here that's totally buried. It's hard to see on the surface, and if you didn't dig down, you know, to see it, you probably miss it. So we got our samples, and what I did was I sampled from basically every 5 centimeters and marked the mark on it, and then for the first 2 meters, and then I took a couple samples every 50 centimeters above, up to 4.5 meters above the formational contact. So now I'm going to sample the Park City Formation below. I'm going to walk over to this ridge over here where I can get at that. I'm going to see if I can find the exact top contact that I was able to sample here, over there, and then work my way down and get some samples just below, so at the very top of the late Permian. All right, this is the Park City Formation, which is very, very different from what we were sampling before. See all this wonderful moss on here. So this is the Park City. So we're actually just stratigraphically below. So this is the surface that I was hitting into at the top, or at the very bottom of that section that I was measuring. So this is the base. I've just walked over from this hillside to get below so we can sample these rocks that are below. And you can see they're much, much harder rocks. All right, I have to carry all these rocks back with me. They're kind of heavy. I'm down in the valley along the creek here, and it's late September, which is a great time to visit this valley because this is when the Sockeye salmon are running up the river keep my eyes open. They're really bright red right now, these fish in this little creek. And see if I can get some on camera. But just a beautiful, beautiful day. Early fall. The leaves are just starting to change. So it's just a beautiful place. So we're back from the field. We got our rock samples. Now it's time to make some predictions and to figure out how we're going to analyze our rocks. So this is what we observed in the field. We have the Permian Park City Formation down here, a limestone represented by a brick wall here. And then we had the Triassic Wood Formation with that basal mudstone that I dug down in there. Now the first thing we can look at will be calcium carbonate. To see how much calcium carbonate are in each of these rocks. My prediction based on the observations in the field is that calcium carbonate will be high in the Park City Formation. It's a limestone, lots of calcium carbonate in it, and then it will drop down in this mudstone layer, and then it will slowly probably rise up a little bit as we get higher up in the Dinnywood when the rocks got a little bit harder than I noticed in the field. Now I'll go ahead and do this analysis in the lab. Now this can indicate two things going on. The older geologists would argue that this is because of rapid rising sea level. Sea level was rising at this time, and so this limestone here basically was a organic reef complex, and it got so deep in the ocean that it got below the photic zone, which meant that light wasn't getting down to the surface. And that meant that many organisms that rely on light couldn't live. And so that usually is a transition from a limestone to shale or mudstone. And so that's what classical geologists have argued at this boundary. This is what's referred to as a drowning unconformity. So rapidly rising sea level caused this transition in the rocks. Another kind of newer idea is that the oceans became acidic. If the oceans became acidic, that meant that calcium carbonate would dissolve out of the water. Now this is really rare when you get into very shallow water. There's usually a deeper depths and more pressure, calcium carbonate often will dissolve depending on the pH of the ocean water. So if ocean waters became more and more and more acidic to the point where no longer limestones could be formed in coral reefs and the coral reefs all died out, then you would get a similar change happening here. So this alone will not rule out our two hypotheses here of what was going on. But there's some other things we can look at. Another thing we can look at here is total organic carbon content, or TOC. My prediction is that we'll see pretty high total organic carbon in the Park City. It will decrease and then slowly increase. This would indicate a decrease in biological activity in the sediments that are occurring here. Now, if ocean levels had risen, we'd actually see an increase of total organic carbon here because there would be more organic material being deposited on the seafloor at this point. So we'd see a spike. So this is one way we can test it very quickly to see, try hopefully distinguish between these two hypotheses. The next thing we can look at that will also help us is delta C13, or the isotope ratio of C13, of carbon-13 and carbon-12. So there's two stable isotopes of carbon, carbon-12 and carbon-13. Carbon-13 is found in all organic things. It tends to like to bond to hydrogen, while carbon-13 likes to bond to things like calcium carbonate. And so it tends to be more bonded to oxygen. So if we see a more C12, carbon-12 isotopes, it would indicate something's happening to the biological organisms living on the planet. Such things as forest fires, burning of lots of organic material getting up into the atmosphere. So usually that indicates a atmosphere rich in carbon dioxide. So if we see this negative excursion in the rocks, which has been seen in other Permian-Triassic boundary sections, then that would be an indicate that we do have the boundary. Now the next one is kind of a new idea, and that is where all the CO2 is coming from and all that's making the oceans acidic, and that would be to look at mercury. Mercury is a sort of a proxy that can be used for the amount of coal that was being burned, and one of the theories is that there were these volcanic fields in Siberia called the Siberian Traps that were releasing a huge amount of coal. They basically were these volcanic eruptions that came down and were burning the coal fields of the Carboniferous in Asia. That released a huge amount of CO2 in the atmosphere, and we can maybe see a spike in mercury. This has been observed up in Canada, in that section up there, and so I'm excited to see if we can observe a mercury signature. And the last thing we can do is to test the idea that it was an impact by a meteorite, and we can look at iridium in the sediments. Now, iridium analysis requires some special machines. We might have to look at some other things as well to try to get at iridium. We're going to do might do a couple samples and see if we can get some of these rare elements and see if they're in there. But if we do get an iridium spike, that would be a first. No one's found an iridium spike at the Permian-Triassic boundary yet, and so that might be something to look at with our samples. So it's time to grind up some samples. So as I crush up these rocks, you may remember I mentioned some black little balls or concretions in the rocks. And as I'm smashing up these samples, I'm noticing that there is those black little, the black minerals are pyrite that's in here. It's a metallic little mineral that's an iron sulfide, which is kind of interesting. You don't typically see in mudstones like this pyrite, but that's what those black specks were. So that's really interesting. Another clue is some pyrite in these rocks. All right, so I thought I'd take you through my methodology for determining the amount of calcium carbonate in each of my rock samples that I've ground up. So I'm using this thing called the carbonate bomb method. It's a method that was developed in the 1970s, and basically what I do is I measure out measuring out 2 grams of my crushed up rock sample onto the scale and get it as close to 2 grams as possible. Then I have this device, a little container here, and I add hydrogen chloride acid, or HCl. But there it is. So we have an acid here that's going to react to any of the calcium carbonate in our sample. So we're going to take our sample, we're going to place it in a cup inside this acid bath of hydrogen chloride acid. Then I'm going to seal it up. Make sure it's nicely and tightly sealed up. And this device here, which is a very simple device, it basically has a pressure release, and it has a detector on here to tell how much pressure has built up into the canister. So I'm going to react these two by shaking it up. And so when I shake it up, then it reacts to the calcium carbonate that's in our rock sample, and it starts to become really fizzy. When it's no longer moving upward, then take a reading. So we're at about 32 kilopascals. Don't know if it's going to get to 35. Looks like it's just hanging there. Measurement. So then I release the pressure by unscrewing this little thing. There it goes. Release the pressure in there. And that's sort of the procedure for measuring the amount of calcium carbonate. So I actually have some pure calcium carbonate, which is right here. So I use that as my calibration. Dissolve that and react that. Take a measurement on that. So I got 90 kilopascals, and that sample I just analyzed, this one, which is 5. I got 32. So then I can use that and get an equation, and I'm also just measuring it, what's left in the thing to see if I can double check my answers. But then I should be able to get a scale that I could use for percentage of calcium carbonate in each sample. All right, so we have analyzed the rocks for calcium carbonate, and we saw that most of the rock, in fact the majority of all of our rock samples, were composed of calcium carbonate, varying from 50 to 90. And we also saw that in the Upper Park City, the Permian rocks, we had high concentrations of calcium carbonate, and above that in the Dennywood Triassic rocks, we saw a lower calcium carbonate amounts in that sort of 60 to 70% range. So the majority of our rocks are calcium carbonate. That's calcium, carbon, and oxygen bonded together. Now what we're going to do is we're going to look for some other things that might be in the rock, and we're going to look at basically 3 things, and that's what this machine next to me actually does. So the first thing we're interested in is the total organic carbon content of each of these rocks, and that's oftentimes abbreviated TOC. Now, organic carbon is a little bit different than the carbon that's bonded to that oxygen in calcium carbonate. Organic carbon is often bonded to hydrogen, and that means that it oxidizes very easily and it makes a nice fuel. So all organic compounds tend to be carbon that's bonded to a hydrogen. It might be bonded to a nitrogen or some other things, but mostly it's going to be hydrogen. And so these compounds actually are slightly different, and they stem from organic material, life. And so this is actually a really neat test to see if we actually have the Permian-Triassic boundary. So if this is the boundary, we should see a drop in the TOC values across our boundary. If this is a drowning nonconformity, we actually see a spike in total organic carbon across the boundary. Now, why is this? Well, if it's a drowning nonconformity, the photic zone the rocks got below the photic zone, sea level rose up, and there would still be organic material in the water column in the photic zone, and that organic material would rain down and start to form layers on top of our limestone. Now those layers are going to be composed mostly of organic content that's raining down, things like little forams and things like that, organic things that are living up in the photic zone, dropping down. And because they're dropping down at such a deep depth into the darkness of the ocean, they start to accumulate. And so often when you see a drowning nonconformity, you'll see a spike in total organic carbon on top of a limestone if the sea level rose and caused a drowning nonconformity. However, if this is an extinction event, there'd be less life existing at that time, and you would actually see a drop in total organic carbon in the rocks immediately above our limestone. So this is an excellent test, and I'm actually really curious to see what our results are. The other thing that this machine does, which will be kind of beneficial, is it gives us a percentage of sulfur. Sulfur also oxidizes, so this machine can analyze sulfur. And sulfur is interesting because as we were measuring and preparing our samples, we saw a lot of hematite and limonite, some of the iron oxides, but we also saw some sulfur oxides. Now, pyrite is really weird because in marine realms, it only is deposited in anoxic environments. That is, in environments in which there's low oxygen. Now, what's really weird about these is we saw sedimentary structures that indicate that these rocks were deposited in very shallow waters. In fact,
we saw interesting sedimentary structures indicating that the wave action was affecting the deposition of these sediments. So the fact that we found some pyrite crystals inside these rocks indicate that maybe these were anoxic environments. Now this machine will give us a percentage of the sulfur content in these rocks, and that'll be something interesting. So we might see a sulfur spike as we move through these rocks. The other thing this machine will give us is nitrogen. I have no idea what nitrogen will do, if there'll be much nitrogen in these samples at all. So that's another thing we can look at in our results. So let me tell you a little bit about how this machine works. And basically what it does is it combusts our rock samples at very hot temperatures, 1,100 degrees Celsius. Then it basically, the atoms that can be oxidized in a stream of oxygen that we're providing it will be oxidized. So the carbon will bond to oxygen, our nitrogen will bond to oxygen, and the sulfur will bond to oxygen. And those will turn into gases, and that will be the exhaust coming off of this, this very high temperature burn. Then those are collected, carried in a carrier gas of helium, and then those are compared to a standard that we also feed into this machine, so it can compare the standard, and then using basically a calibration, it figures out how much of organic carbon is in there, how much sulfur is in there, and how much nitrogen is in there. Now basically this machine works is we have an auto sampler in the top, and I got to measure out teeny tiny little bits of our rock to feed into this machine to have it analyzed, and we'll see what the results are. So this is a really nice curve. This is what's called a chromograph. And so each of these peaks represent different elements that we're looking at. So this first little teeny tiny peak here is nitrogen. We don't have very much nitrogen in this sample. This big huge one that goes all the way up to the top is quite large. That one there is our carbon. So a fair amount of carbon in this. That's organic carbon. This little bump here is our hydrogen. And then this bump back right there, that's our sulfur bump. The interesting thing is when we look at our data that we're getting of total organic carbon, what we see is a dramatic drop in total organic content percentage. So we started out with around 15%, and we dropped down to about 3%. And it's a pretty dramatic drop that you see right at that boundary between the latest Permian and the earliest Triassic. So this is indicating that something else is going on. So we're seeing both a drop in calcium carbonate and a drop in total organic carbon. This is telling us two different things. The drop in calcium carbonate seems to be indicating that we have an acid ocean, so an ocean that's becoming acidic, hence the calcium carbonate can no longer be deposited and is being sort of absorbed by the acid in the ocean. The drop in total organic content is because of the lack of organic organisms as you enter into the earliest Triassic there. And so you're not getting a big input of organic material into the system, and so you see a dramatic drop. This is indicating something different. This is not an unconformity. To uncover the carbon isotope ratio and other more advanced tests, I traveled from the Uinta Basin campus in Vernal to the main Utah State University campus in Logan. Here, at the geology department, I'll run further tests on the collected rock samples. All right, so I'm still in Logan. I've been here for 3 days, running, basically getting all the samples up and running. Tonight we're basically the third night. We got the mass spectrometer to run our carbon isotopes. So the little machine with the little arm moving back and forth is working away. It's about 10 minutes or so to do each sample. So by tomorrow, hopefully I'll run through all of our samples, and by hopefully early next week, we'll have all of our numbers. So now it's just waiting, which is, I think, one of the hardest parts to this is waiting. The ICP-MS, we're going to have to wait probably another week for those to run. They have to evaporate out. and then add them into a solution, and then compare those to a standard. So those will probably be run in about a week. The mercury I sent away, and we got 4 samples back, which are all very positive. And so I'm waiting to get the rest of our samples back. But the first 4, I included one that was right at that boundary with that limestone, right at the base of the Diniwood. And that one proved to have high concentration of mercury. So that seems to indicate that there's a spike in mercury, which would indicate that the boundary is right there. So I'm hoping that we'll get our carbon isotope soon so we can confirm that. Now it's just waiting, and that's the hardest part about all of this. You can do all these science things, you just gotta wait for the data to come in, and then you gotta kind of scratch your head when the data comes in. We got a few numbers off the Mass-Spec before I left the lab tonight. They were kind of all over the board. I'm a little bit worried about some of our methodology, and if it tends to be wonky, that might be something I have to address. And rerun some of our analyses, and if it does come back that might be the problem, which I don't know because I only got 3 numbers, and yeah, so I'm just kind of like guessing in the dark right now. But I gotta wait for the data to come in, and so I'm gonna head back to Vernal tomorrow. Hopefully we'll get all the data emailed to me from Logan, and we can then take a look and see if we do have the Permian-Triassic Boundary.
Why am I doing this? Well, depending on how you count up the species that died, between 70 to 97% of the species on the planet went extinct at the Permian-Triassic Boundary. Geologists call this interval of Earth's history the Great Dying. It was a period of death. Trilobites, a previous diverse group of arthropods, vanished, all of them. Brachiopods, a group of shelled organisms resembling clams, nearly completely vanished, with a single genus pushing through the boundary, Linguinea, still alive today, burrowing deep in offshore mud. Rugosa, the most common of the coral fossils, absent, gone, victims of this extinction. Tabulata corals, all dead. For millions of years afterward, the oceans contained no coral reefs. Crinoids, common stalked echinoderms related to starfish, flourished in the oceans, but death came to them as well, as millions succumbed to extinction. A tiny fraction survived into the modern ocean as sea lilies. On land, most primitive spore-bearing plants and trees, dead. Only a few ferns and horsetails made it through, as well as plants that bore tough seeds to regenerate after the disaster. The death of Earth's forests meant that coal would no longer form in the Triassic. Our own ancestors, the synapsid reptiles, dead. But a few species escaped death, including the small pig-like Dicynodont, Listosaurus, and the tiny-haired mammal-like cynodonts persisted. Mammals no longer would be large, bulky beasts, but scurry in the darkness like tiny mice into the age of the Mesozoic. The ancestors of turtles, dinosaurs, birds, the diapsid reptiles, would fare slightly better, but the amphibians would perish en masse. All amphibians of today, the frogs, the salamanders, the caecilians, are all descendants of a tiny group of survivors unique in their ability to metamorphose from a tadpole during their lifespan. The basal Triassic rocks are a wasteland of death, as almost nothing survived the mass extinction. Those species that miraculously made it through would go on to rule the Earth for the next 252 million years, including our own lineage. But who was the killer of species, and what was the weapon of these killings? I think we need to find out who this killer was.
Why does pyrite in my rock samples frighten me? Well, it's mid-November, and I'm still waiting for my isotopes and other test results to come in. In the meantime, I've been having nightmares about pyrite. Pyrite's one of my favorite minerals. It's metallic and shiny, and it often forms these beautiful cube crystals. And pyrite's composed of iron and sulfur bonded together. Its formula is FeS2, which means there's 2 sulfur atoms, S, bonded to each iron atom, which is actually abbreviated Fe. The problem is how does pyrite get into sedimentary rocks? How does it form? Experiments in labs have shown that pyrite forms when H2S, that's a hydrogen sulfide, reacts to iron. But this only works without the presence of oxygen, because otherwise the 2 molecules would react with the oxygen instead, producing iron oxide minerals like hematite, limonite, goethite, and the sulfur would react and become a sulfate with oxygen. If you want to make pyrite in a lab, what you need to do is you need to have an oxygen-free environment. So when you see pyrite form in marine sedimentary rocks, such as the rock samples I prepared, it implies that there was little to no oxygen present during the deposition of those rocks. Now, an ocean without oxygen is what we call a dead zone, an anoxic ocean. Anything that needs oxygen for respiration can't live in those waters, which includes most animals. This type of nightmare ocean is called a Cadfield ocean after the Danish geologist Donald Canfield. The sedimentary structures they observed indicate that this Permian-Triassic ocean was an anoxic vent at very shallow depths. The geologist Okio Ozaki was the first to propose a major anoxic event as a driver of extinction with his classic study of the Permian-Triassic Boundary in Japan. So the same thing is happening on the other side of the Earth here in Utah. This anoxic ocean was global. But it leaves us with a question. Where does the hydrogen sulfide to form this pyrite come from? And this is where things get scary. In the rock samples that I've collected across the Permian-Triassic Boundary, sulfur begins to appear 70 centimeters above the lithological boundary. This sulfur is in the form of small 5 to 10 millimeter pyrite framboid crystals, the same type of crystals that form when pyrite is made in a lab with hydrogen sulfide gas. The pyrite framboid layers appear to represent cyclic events of anoxia. Hydrogen sulfide gas is a toxin, but naturally produced through microbial chemosynthesis by a group of bacteria called sulfate-reducing bacteria. And these bacteria, they eat the dead, using sulfur to convert methane produced by the decaying organic matter into compounds that allow them to grow and reproduce. They exhale as a waste product this hydrogen sulfide gas, which accumulates in the oceans and lakes, even today's oceans and lakes, anywhere where there's lots of dead things. They can also be found in underground aquifers feeding on oil and natural gas. The flares you actually see in oil fields are often composed of hydrogen sulfide gas produced by the bacteria living deep underground. With the mass extinction, all this death on the planet produced an overabundance of decaying organic matter, dead bodies. And these sulfate-reducing bacteria gorged themselves on this oversupply of a food source and released large amounts of this gas as their populations exploded. These bacteria don't need oxygen, and they seem to have flourished in the anoxic ocean filled with the decaying dead from the mass extinction. Hydrogen sulfide can react in the water to make it even more acidic with the freed hydrogen ions. And this may be why I don't see carbonate levels return to normal in this section of rocks here in Utah as I first predicted, as the ocean remained acidic well into the early Triassic. If this toxic hydrogen sulfide gas gets into the atmosphere, it kills any animal that breathes it in. Just a tiny fraction of gas, between about 10 to 500 parts per million, is deadly. So it's really deadly stuff. And the Permian-Triassic Boundary just reeks of it. As the hydrogen sulfide gas oxidizes in the atmosphere to sulfur dioxide, it results in acid rain. And that acid rain then kills the forests that were living at the time. This pyrite, those black nodules that I first described in the field, they're the stuff of nightmares. So I got some exciting news to share with you. We have our carbon isotope data, and I thought I'd go over our data. It's very preliminary. We don't have all our samples run. We had some technical issues with the mass spectrometer, but I thought I would go through the data and we can compare it to what's been observed in China. So this graph here is the data from China across the Permian-Triassic Boundary. And you'll notice that there is values, is kind of a curve here. So the values start out positive between about 3 and 4, and they decrease all the way down to like -2. So let's compare that with the data that we have collected, our preliminary data. See if we're seeing the same thing. So here's our data. So we have values around 2 and 3 down here in the Upper Park City. And then we notice that they're decreasing and getting down to like -3, around -2. Hopefully we'll get some more data. But this trend here of going more negative across the Permian-Triassic Boundary is very similar to what's been observed in China with their carbon isotope record. All right, we got all the mercury data in today, and I'm super excited to show you this. All right, here is the raw data. It's in parts per million, and it's clear that there are elevated amounts of mercury in the rocks near the boundary. All right, so this next graph, I've taken the amount of mercury and I divided it by our TOC percent values. This is to factor in the fact that mercury is also associated with organic matter. So rocks rich in organic matter have higher levels of mercury. When we take this into consideration, we can see that the mercury-rich layer is really confined to the first 70 centimeters at the boundary in our section. Now, previous researchers have argued that this spike in mercury at the Permian-Triassic Boundary is a result of fallout from the atmosphere due to widespread burning of coal with the expansion of the Siberian Trap volcanic province in Asia. So this spike in mercury supports the idea that there was large amounts of coal combustion during the interval of the Permian-Triassic mass extinction, likely set aflame from a large volcanic eruption. So I've been looking at the results of our nitrogen, which I've not shown you yet, and I've discovered something very cool. In the Park City limestone, values of nitrogen vary widely, and this is because the limestone represents biologically active normal shoreline deposition. But the nitrogen percent in the basal 200 centimeter layer of the Dinnywood Formation is found to be in a very narrow range. Now, the reason is that nitrogen was not being utilized by marine life after the mass extinction. And this narrow range was influenced not by organisms which use nitrogen for growth and reproduction, but by inorganic processes, such as the seasonality due to the orbital cycle of the Earth. So if we look, we can see there's kind of 3 cycles of nitrogen values, sort of kind of decreasing, then suddenly increasing, and then decreasing within these narrow range. Now, I think that these 3 cycles that we see in the nitrogen values represent Milankovitch cycles in the Earth's orbit, and in particular, the duration of the precession cycle, which lasts about 23,000 years. Now, if that's true, then we can add a temporal scale to the length of time it took to deposit these layers of rock. Now, there's evidence from the stratigraphic section in China to corroborate this idea. Seth Burgess at the USGS and colleagues at MIT have found fresh zircon crystals in 2 layers in the stratigraphic section in China, which yielded 2 radiometric dates separated by about 61,000 years. Now, if we compare the carbon isotope values between the Utah stratigraphic column with the one in China, we find a similar rate of decrease of isotopic values between those 2 beds that correspond to the layers in Utah between 0 centimeters and 170 centimeters, which closely matches our nitrogen temporal calibration of 61,000 years. So, it does look like this nitrogen variation, these very small variations in cycles, are due to orbital variations. All right, so then using this temporal scale, then we can measure the length of time it took for the acidic oceans to turn anoxic at shallow depth. So that's about 20,000 years, with the oceans becoming acidic in less than that time. But to find out how long, we need to compare the onset of the mercury spike with the nickel spike, representing ash from the volcanic eruptions. And we're still waiting. We're waiting on the results of our ICP-MS, which measure nickel content in the rocks, and we need that before we can tell. So it's been 2 weeks since I got the full data set back for the ICP-MS run, and it's mid-December, and I wanted to share with you some of the findings. Now, the reason that we did this test was to look for evidence of 2 possible causes of the Permian-Triassic extinction. The first is an extraterrestrial impact event, and the second is a massive volcanic eruption, and see if we can find traces of volcanic ash in our examined layer of rocks. Now, I didn't get iridium numbers because the lab didn't have an adequate standard, and iridium is actually so very rare that samples actually require extra methods to be able to detect such small amounts. What we did get was a number of other siderophile elements. Siderophile elements are elements which are attracted to iron, but they're also drawn down into the core of the Earth, and hence on the surface of the Earth they're depleted, or they're fairly rare elements. So a large spike in siderophile elements in our samples could come about if there was an asteroid that actually struck the Earth and distributed these rare siderophile elements, acidophile-rich dust around the world. So high values of siderophile elements were actually used to discover the end Cretaceous extinction. So did we pick up any evidence of an asteroid impact? All right, guys, you ready for it? So here are the 6 siderophile elements: chromium, cobalt, nickel, zinc, palladium, and platinum, and none of our samples across the Permian-Triassic boundary here in Utah show any elevated amounts in the range of those observed at the end Cretaceous event, which would be in that pink zone there. In fact, there's no evidence from any of the known Permian-Triassic stratigraphic sections for high levels of siderophile elements at high enough concentrations to reflect an extraterrestrial impact event. And we see that here in Utah too. So we can rule out an asteroid impact as the cause of the Permian-Triassic extinction. So what about the idea of a supervolcano? In this case, we can then look at nickel. Now, nickel is a siderophile element, and volcanic ash also contains elevated amounts of nickel due to its richness in rocks deeper in the interior of the Earth. So if there's a layer of volcanic ash enough to darken the skies and cause a global mass extinction, we would expect to see levels of nickel above about 250 parts per million. So let's see if we got any volcanic ash in our samples. So nickel that we found is only slightly high. It peaks at around 60, and that's if I combine the two stable isotopes of nickel. So we don't see much copper either in these samples. Another element that's associated with volcanic ash. Nickel is only slightly elevated, and this is likely due to enhanced chemical weathering. But it's not the levels you'd expect with a massive big volcanic ash layer. So we don't see any evidence of volcanic ash in our Permian-Triassic Boundary section. So it doesn't look like it was a super giant volcano that caused the extinction either. So we've already saw that there was elevated amounts of mercury in our sample. And mercury is found in abundance in coal ash, particularly Paleozoic coal. Mercury bioaccumulates from the atmosphere into plant tissues. And when those plants die and they become buried, they form coal and they sequester mercury out of the atmosphere. However, when large amounts of coal is burned, the mercury is re-emitted back into the atmosphere, which can be then detected in sediments. Another element that behaves like mercury is zinc. Unlike mercury, zinc is actually a micronutrient which is needed for plants to grow. And it's actually absorbed into the plant tissue. And strangely enough, if we look, we see elevated zinc across the boundary, which has also been observed in the stratigraphic section in China. Coal ash also contains an abundance of lead. And if we look at our lead levels, we see that during the entire duration of the carbon isotope excursion, we see elevated amounts of lead in the Permian-Triassic boundary section. But perhaps the biggest peak that we see is actually with strontium. Now, strontium is more abundant in coal than volcanic ash, but it can also be leached from the soils when subjected to acidic rain or acid rain. All right, so across the Permian-Triassic boundary, we see elevated evidence of carbon dioxide with more acidic oceans. We see more carbon-12. We see an abundance of mercury. We see lead, zinc, and strontium peaks. These are all signs of a massive combustion of coal. This black region that appears on Google Earth is the Siberian Traps. It's a vast field of basalt formed from the eruption and flow of lava dated to the time of the Permian-Triassic boundary. And next to this region is the Tunguska Basin, which contains a network of sills where magma heated the rocks above, which contain thick layers of coal, but also other fossil fuels like petroleum reservoirs. On a foggy London winter, on December 5th, 1959, the air became unbreathable. The onset of winter and cold weather resulted in many homes to stoke up the fires and burn coal to stay warm, as they had for a generation. But something was going to happen over the course of that dreadful week that resulted in the death of 12,000 people and affected the health of 100,000 more.
Special filtering bunny masks are the latest weapons devised to combat smog, which last winter killed 4,000 Londoners in a single week. Dogs as well can be protected against the deadly fumes, which throw a heavy pall across Britain's big cities every year. Ordinary fog does little harm, but smog has become one of the greatest mass murderers of modern times.
As the air filled with the soot of burning coal emitted from chimneys of the growing large megacity, an inversion of temperatures trapped local carbon dioxide, organic volatiles, mercury, lead, strontium, and zinc. But something was trapped in the air. Lots and lots of sulfur. Sulfur is oxidized during the burning of coal into sulfur dioxide, or SO2. Now, SO2 gas dissipates into the atmosphere, but if the air is humid or foggy, such as in London, the sulfur dioxide reacts to the water and nitric oxide, which is also produced by coal combustion, but also automobile exhaust, with water in the atmosphere. This produces sulfuric acid, and this is the chemical equation. Now, this little AQ down here means that the sulfuric acid is contained in the water vapor. And if this water vapor is breathed into the lungs, it's highly corrosive and will result in coughing, shortness of breath, difficulty breathing, and finally, death by pulmonary edema, that is, fluid filling the lungs. Birds fell from the sky, dairy cows died in the fields, stray cats and dogs lay dead in the city streets. Children were rushed to the hospitals, and doctors saw their patients die before their eyes. Sulfur was the killer. Medical scientists today estimate that sulfuric acid and other air pollution kills an estimated 6.5 million people every year. If the Permian-Triassic Boundary was brought about by the massive burning of coal, we need to find out what happened to all the sulfur. In our section of rocks, we noticed that pyrite, which contains sulfur, formed not in the lower boundary of the section, but higher up, whence the oceans had become both acidic and anoxic. So we need to figure out how to convert SO4, this is our sulfate or sulfuric acid, into FeS2, this is our pyrite, as massive amounts of sulfur was dumped into the world's oceans. This conversion would take place over 20,000 years and require two types of bacteria and would profoundly change the nature of the oceans. Step one requires removing the oxygen from the ocean. Once the ocean becomes acidic with the absorption of carbon dioxide, such as that found in soda water, shelled organisms die. And it doesn't help that there's large amounts of sulfuric acid also being added to the ocean from the atmosphere and rainwaters. Now, these dead bodies begin to sink down into the depths of the ocean where they are decomposed by anaerobic respiration. And here's the kind of the simplified equation of this. For this chemical reaction to work, you need oxygen. And it produces more carbon dioxide. And that carbon dioxide then makes the oceans even more acidic, and more organisms die and start this equation over again. However, as the atmosphere and climate became hotter and hotter with all this excess carbon dioxide, the oceans themselves also became hotter. Now, warmer water can't hold as much oxygen as cold water can. And slowly, the oxygen gets used up in the world's oceans. This is the realm of the sulfur-reducing bacteria that use SO4 instead of oxygen. But there's a problem. The oceans at this point are also pretty much exhausted of dead bodies by now. This was pointed out to me by a colleague at the University of Iowa, Dr. Swanner, who noticed that my TOC percent did not peak with the sulfur. Now, typically there's a positive correlation between high sulfur in sediment and high organic matter, but I didn't have that. I had low TOC percent and high sulfur in the form of pyrite. There had to be something else going on in the oceans. There's one element that does peak at the sulfur layers: barium. So barium peaks at each of the pyrite zones but one. But why? Why does barium peak when we're seeing the pyrite? Well, barium likes to bond with sulfate,
and it forms a mineral called barite. And its chemical formula is this. This doesn't explain where this barium is actually coming from. If there's any of this in here, obviously it's going to form barite. But why? Where is that barium coming from? In a normal oxygen-rich ocean, SO4 hangs out at depth along the seafloor. As sulfur is oxidized from microbial processes, they're using H2S in the sediment. And so this is producing the sulfate here. Now, if there's any barium that's coming up from hydrothermal deposits, barium ions, they're dissolved in the water, they're going to quickly react to that sulfate, and they're going to produce our barite. Now, the barite is going to precipitate out as these little crystals, and those crystals are going to accumulate on the ocean floor down here. So we'll get a whole bunch of barium accumulating at depth. So if we are seeing barium up here in our section, in the shallow marine section, it must mean that somehow this barium was upwelded into the ocean to then accumulate in those zones up here in the shallow ocean. So as the ocean continues to warm and it gets hotter and hotter, there's something else deep in the world's ocean. There's something called methane hydrate. It's a solid form of methane, which is the same stuff as natural gas. It's carbon bonded to 4 hydrogen. It's locked in a lattice of water molecules called cathrates. And if the temperature gets warm enough at the base of the ocean, these cathrates begin to sublimate into a gas. This gas of methane begins to bubble up from the depth of the ocean. And this will bring methane gas up to the surface, up to the surface wires that I'm seeing here. But it's also bringing barium as well. With this abrupt upwelling of methane into the ocean, the sulfate-reducing bacteria now have an energy source. So this is what the sulfate-reducing bacteria are doing. They're taking the methane and the sulfate in the aqueous solution in the ocean, and they're converting it. And we can now follow the sulfur through this process. So it's converting it, it's bonding it to a hydrogen. At this point, we have HS. This HS is then going to bond with the hydrogen, which is plentiful because we have acidic oceans, and it's going to form H2S. Now, H2S, of course, is toxic. It's a toxic gas that's going to be produced in quantity. This H2 gas then, in our reaction, is going to come in contact with sediment that has iron in it, often bonded to some sulfur. And in this, when it comes in contact with that sulfur, if it doesn't bubble out of the oceans as a gas, it's going to form FeS2, or pyrite. And that's how we get the sulfur through the system. What we're witnessing with each of these pyrite horizons, these pyrite layers, is the upwelling of methane hydrate. Methane is a greenhouse gas. And once in the atmosphere, it not only keeps Earth's heat from escaping into the atmosphere, it also oxidizes and produces even more carbon dioxide. We had on our hands a runaway greenhouse event.
Ocean temperatures calculated across the Permian-Triassic Boundary in China indicate temperatures like you would find in extremely warm hot tubs, 110 degrees Fahrenheit and 43 degrees Celsius. At these temperatures, proteins denature. The entirety of life on the planet was on the brink of ending forever. Now, not all life died at the Permian-Triassic Boundary. A few things survived. But how do you survive the end of the world, such as indicated in this lonely layer of rocks in Utah? What of the 3% that survived? Well, on land, the plants that survived are the plants that have seeds, hard seeds, and that develop the abilities to survive with very limited water to reproduce. So pollen-borne plants did well with seeds. Animals, like our own ancestors, burrowed in the ground. And by burrowing, they were able to hide out, and they were also probably stored food reserves that they could then feed on. But the oceans, I mean, what of them? Well, here's the thing. Have you ever wondered why the salmon are swimming up the rivers to spawn? What are they running from? Why fertilize their eggs in shallow but well-oxygenated rough and tumbled waters and then die? Why not just stay in the safety of the oceans? The early bony fish, the ones that survived, ran away from this deadly ocean up the rivers and streams into the cool, oxygenated waters. Today, when we see fish running up these narrow rivers and streams, they're replaying a harrowing escape first attempted 252 million years ago, a behavior that has allowed them to survive the great disaster in Earth's history. After the Permian-Triassic Boundary, this ancient strategy and those amphibians with swimming tadpole larvae had a unique success rate. So today these creatures, the fish, the amphibians that metamorphize, the reptiles, the mammals, the surviving land plants that are around us, they owe their success to how they made it through the end times of the Paleozoic. All right, it's late February, and I've been hard at work writing up a manuscript to send off to publish of our scientific findings that we made with this episode of The Rocks of Utah. I've also uploaded a preprint of all the scientific data, the charts, the figures, put it all together, and you can take a look at it. There's a link in the description below, and read it over. I'm sure that this research is going to elicit a lot of comments and suggestions and ideas and spur a lot more interest in the Permian-Triassic Boundary, and I hope it does. So take a look at it. If you have any suggestions, any comments, please feel free to let me know. I also have started a Patreon page that you should check out. And I want to thank all of those viewers out there who have contributed some money to my Patreon account. So check it out. There is some really cool exclusive features, including a really cool trailer that I put out a couple weeks ago on this very episode of The Rocks of Utah. So check it out. Drop a few dollars into the little tip jar there on Patreon and help support this channel. Thank you for watching this very long episode of The Rocks of Utah. I hope you enjoyed it, learned a little bit about the Permian-Triassic Boundary, and I look forward to seeing you in the next episode of The Rocks of Utah.